All right, so after some amusing adventures attempting to start this talk, what do you mean my laptop won't charge? We are here, and we are here to talk about more strange tricks against networks, the ye old black ops of TCP/IP. Yeah, after 4 or 5 years, maybe I should come up with a new name, but whatever. So, who am I? I do stuff. What am I here today? The slide is there for people reading. You guys get data. So what are we here to do? Like 5 seconds of MD5, bash on some IP frags, poison some name servers, mess with Sony, flood ginormous amounts of traffic across the entire internet, and by the way, pretty pictures. So, how many people here were here for my talk last year on MD5 collisions? You guys rock. So there's some updates. We actually have an MD5 collision generator. Stock and Lou went ahead and built one. The code is about as obtuse as humanly possible, but is absurdly optimized. You can go ahead and get it at that URL. And I actually released my tool that goes ahead and takes their collisions and is able to make any 2 web pages have the same hash. So go ahead, go to DocSparrow.com, grab the code. It all works quite well. You feed it 2 URLs, it feeds you 2 web pages with the same hash, but the content of each URL. So, fun. On to new material. IP fragmentation. So, fragmentation, an interesting early architectural error that shows how much experimentation was going on while IP was being designed. This is engineer speak for, what the hell were they thinking? It's actually a general idea. You see this reinvented time and time again. The idea is, well, I've got some packet, and it's this big, and I've got this network, and it can handle packets this big. I can either send nothing, or I can chop this thing into little pieces and send them along. Sounds like a great idea. Why wouldn't it be? Well, IP's whole idea is that you got some data and you send it, and you don't need to keep track, and you don't need to think. You just got stuff and you fire it along, and something else will take care of things if they drop. Well, the problem is with fragmentation. If you're sending fragments, whatever, I've got 100, I've got 5 fragments, I send them off, I don't care. But the receiver, well, he has to receive the first fragment. And there's a bunch of other fragments that may or may not come in some arbitrary order, may or may not come with some arbitrary overlap. There's about 1,000 different ways that a packet can be fragmented, and while over time all these ways resolve themselves, the receiver has to keep stuff in memory and has to dedicate resources and has to figure out which packets, which fragments align with each other fragments. It's a mess. It completely destroys the idea of IP being something that is fire and forget. You send, you receive, the entire world is at the packet basis. So there's a bunch of history here. Shockingly enough, using fragments was actually a great way to get around intrusion detection systems. Tim Newsham and Tom Patchak back in '98, this is 7 years ago, went ahead and came up with pretty much a classic in the security field called insertion, evasion, and denial of service, eluding network intrusion detection. And they basically destroyed the entire field of devices that claimed to be able to look on a network and see what traffic was going on. They did such a thorough job that pretty much for years and years, there wasn't another attack that was publicly found that they hadn't iterated across and was eventually implemented in Doug Song's frag router. So, I mean, really, they really did a rather thorough job. In fact, most of all of layer 3, most of IP and even TCP has been picked clean by the security community. It was really seeming like there was absolutely nothing else to find. So, me being someone who likes to try to find stuff, and there really wasn't anything left, I started thinking, well, is there possibly something? Well, around the time where I was looking to create my new talk, there was a bunch of stuff going on in the crypto world with timing attacks. Dan Bernstein went ahead and found out that if you timed precisely how long it took for the AES encryption algorithm to encrypt certain blocks, and you did this over and over and over again, eventually you'd find the key. Yikes, that really wasn't expected, but it was part of the optimizations. No one had considered that there would be a timing channel into figuring out what was going on inside the system. And so I started thinking, are there any timing channels inside of IP? And it's like, well, yeah, there's fragments. It turns out that there's something called the IP fragment reassembly timer. Things are only going to wait so long trying to reassemble your data before they give up and say, okay, you know, forget it. I've been trying to reassemble this packet for 30 seconds. I give up. I'm not going to dedicate any more resources to reassembling this data. And so this timer differs from operating system to operating system. Hey, great, you know, 83rd way we can detect the difference between a Linux box and a Windows box. Woohoo. But I started thinking, you know, could we possibly evade intrusion detection using the fact that different systems are going to have different timers? And I thought about, well, okay, well, what if the IDS holds stuff along for a different amount of time than the host? Okay, well, if the IDS expires their fragments, if it gives up first, this is not a hard problem. Okay, so the host will accept fragments for 30 seconds, and the IDS will accept fragments for 15 seconds. Guess what? I send it too slow for the IDS, but fast enough for the host. I win. Not a problem. More interesting is if, and of course this happens. I mean, this is straight up what happens with Norton Linux. There was an interesting... Actually, no, forget it, but okay. Well, what do you do if the IDS actually has a longer timer? And actually, in general, the IDS will have a longer timer because IDSs want to keep things around just in case they're useful for later. You know, they don't want to be throwing stuff away too early and then, you know, they needed it and then they didn't have it. So they'll tend to be robust. They will tend to err on the side of having too much material. Well, how can we attack that? Well, here's what we're going to do. Well, our problem is an IDS is keeping fragments around for too long. The solution is, well, let's make the IDS drop some fragments. Well, we need a strategy here. How do we make IDSs drop fragments? Well, they leave the reassembly queue when either they aren't reassembled because it's been too long, or when they are reassembled, when it did work, when everything worked just like it was supposed to. So, is it possible to give the IDS something to reassemble against, but without causing the target host to have the same reassembly? And the answer is yeah. We use a timing attack. And here's how it's going to work. Well, first thing we're going to do is we're going to take a look at, say, 2 web requests. One of them, totally innocent, no problem. It's just a get slash. Hi, how you doing? I want, you know, your default web page. Okay, the other one's SQL injection. Now, if you look at a SQL injection attack, or you look at what I have up there, MSADC, that old thing, which shockingly enough still actually works in places, if you look at them, they have the same header. They're both starting with HTTP 1.1 get, and we want the IDS to see, just get an index. And we want the host to see this MSADC attack. Shared payload, or shared header, but 2 different payloads. One of them safe and one of them malicious. So let's look what we're going to do here. The first thing we're going to do is we're going to send the payload that we want the intrusion detection to see. We want the intrusion detection system to see the index.html payload. And we send it. And then we wait. And eventually, you know, what happened? The IDS got it, the host got it, but we waited. And the host dropped it, but the IDS kept it around for later, just in case. So now we send the shared header. And what the IDS says is, well, it's got its header, and it's got its payload, reassembles just fine, no problem. But the host, it already dropped the innocent packet, so all it's got is a header. And so the host is just keeping that header around for later, just in case it's useful. We make it useful. So now we go ahead and we send the MSADC attack, and that payload attaches to the header, reassembles in the host, no problem. But what does the IDS do? Well, the IDS already dropped the header, so it doesn't reassemble anything. So, long story short, yeah, differential timers, bad thing. And I actually tried to draw a pretty picture of this. I'm not very good at hand drawing pretty pictures, let me tell you. But I mean, it basically looks like the same packet gets sent, gets dropped at the host, but kept around for later. It's assembled at the IDS, so that's what that blue thing means. up top, you'll see that that message gets held around for later. We do another packet transmission up there, and it's like, okay, well, I've got both, but the IDS has nothing. The IDS keeps that last MSADC payload around forever. Or actually, it ends up dropping it out because it's never going to get the header again. So that's the game that you play. Now, some IDSs are going to block this. They will notice actually that the IP IDs actually do need, IP has an identifier field that is used so when you get multiple fragments, you're able to go ahead and assign them to the same packet ID. That's what the IP ID is. And some IDSs, even when they do reassembly, they will note the recently used packet IDs, the IP IDs, and even after the fact, they'll store that around. So there are actually intrusion protection systems that are going to go ahead, detect this, and suppress it. Good for them. Unfortunately, you'll see very often on these very same intrusion detection systems that they got this great idea. And what was their idea? Hey, you know, there's a lot of IP addresses on the internet, right? Let's just block the ones that are doing bad things to us. That'll be great. Because, you know, it's a business case. So we drop 0.01% of the traffic on the internet. If 0.01% of the traffic causes 80% of the problems, then you know, business case, so you lose a few customers in return for, you know, much less headaches. Sounds like a great idea. You know, you can just hear the business guys congratulating themselves on their brilliance. There's a little problem with giving the outside world access to your firewall rules. It's amazing how much of the internet I could have killed the other month. Okay, really bad things happen if you can't access the DNS root servers. Like, DNS doesn't work. And if DNS doesn't work, kind of nothing else does. So, you know, I recently sent out huge amounts of name server traffic. I'll be mentioning some of the details about it later. But there are networks that just don't talk to me anymore because they're like, well, you flood traffic, and I should kill you for that. It's like, I could have pretended to have been the name servers, and you would have done that automatically. It's not a good thing. Now, here's the deal. Yeah, that's cool, but it's been talked about, it's been whispered about, it's kind of obvious, and here's the big problem with that attack from an attacker perspective. When the internet goes down, people tend to notice. So it's not going to be a long-lived, long-term effective attack. But there are other name servers besides the root servers. There's somewhere between 3 million and 9 million name servers active in the world. And these name servers actually can also be blocked. Now, I've been investigating DNS poisoning. That's actually what got me into doing a lot of this research in the first place. And I started thinking, is it possible, given networks that are implementing automatic network shunning, not to just turn off the internet, but to poison name server caches and selectively hijack network traffic? And the answer is, yeah. The general theme is to block communication between any two name servers. Now, you might think, okay, bad, you know, targeted denial of service. This ISP can't access this bank. No, it's much worse. Much worse is a DNS poisoning attack. If you have a situation where requests are going out, normally, let's say you're trying to be a bad guy and you're trying to fake your replies to a given site such that that site thinks that you're the name server and you're providing, you know, the IP address for a given name. You're going to try to, you know, beat the other guy. You're in a race with the other guy. But the other thing is the other guy has all the information he needs. He knows the source ports. He knows the transaction IDs. You have maybe this 100 millisecond window in which a request goes out and you have to get the right response back, and you have to get all your fields right, and you have to do this in a couple 100 milliseconds. Yeah, good luck. But if you go ahead and you cause an automatic firewalling of the other guy's name server, it's like you're in a race, but you kneecapped the other guy. He's like hobbling along, and you're just flooding traffic all day. You win. So The general idea for how that works is it turns out you can kneecap either side. You can either cause the servers to be unable to see the clients or the clients to be unable to see the servers. Now, first model. Spoof malicious traffic from the client network to the server network. You'd have some podunk ISP, and you basically have a bunch of traffic that gets spoofed against the bank network. The bank eventually says, you're a business risk, I don't need to talk to you, stupid little ISP. Now the ISP is sending out all these requests, none of them are getting responded to, all the time in the world for fake responses to go ahead and get pushed in. In fact, because of DNS recursion, generally you can just go ahead and continually cause a name server to make outgoing requests, and thus with all these outgoing requests you have continual opportunities to get your fake responses in. And because you never have an actual successful response get through, you never have an issue where information gets into a cache, you just have permanent availability to keep on flooding. It ends up taking an average of 65,000 packets. Actually no, 32,000 packets if they have a fixed source port. So 32,000 packets, and you have hijacked an arbitrary institution. This is not good. And mind you, this is being brought to you by the power of crappy security technology. I'm not someone who normally comes up here and talks about how you can go ahead and attack things. But I have no patience for anyone and anywhere that's going to sell bad security equipment. You know, if you're actually putting money into security, it damn well better make things better. So, the other side of that, thank you, by the way, spoofing malicious traffic from the server network to the client network. This would be some ISP. It's like, oh my God, the bank is attacking us. Block, block. We paid our bills. Now here's what's funny about this variant. Because you would think, well, the client network, you know, so it can't see the bank. How come it can see your spoofed replies? Because wouldn't your spoofed replies also look like they're coming from the bank? Funny thing about DNS. See, you've got all these name servers, and sometimes they have multiple IP addresses, and sometimes they forget to send the reply to the same IP that you sent to. And so the name servers have all been written where they don't actually care who's talking to them. They just want to see the right IDs. So you actually get this hilarious little situation where everyone in the world can respond for the bank, just not the bank. Crap. So, moral of the story, do not give the world access to your firewall tables. Disable anything that even smells like automatic network shunning. So, how have I been getting automatically network shunned around the world? I got me a new toy. It's great. It's got a huge amount of bandwidth. It's like 170 gigabit. Turns out there's this network that deals with DDoS attacks, these Prolexic guys. And they have a gigantic amount of spare bandwidth. Because the funny thing about DDoS is if they don't work, they don't continue. Because you're just wasting your money. So these guys basically have a network that eats DDoSes for lunch. They're a third-party firewalling service. They're awesome. And usually their bandwidth is not being used that heavily, so I get it. They've been very helpful. I worked with them on something called the Opti project a while ago to map the internet, and that actually was a huge success. So walking around Vancouver, I'm like, that huge poster on the side of that building looks a little familiar. So I've been using their net to probe the internet's DNS infrastructure. Been working with some guys over at Cisco. Been working with Sebastian Kramer, who's actually, is he in the room? Sebastian rocks. Say hi to him later. And maybe you. I mean, I have a huge amount of bandwidth, and I'm out to do good things with it. So if any of you have an idea of what we can do if we, with real visibility into the network, let me know. I'll see what we can do. I've been doing exceedingly large-scale scans, every IP, every name server, everywhere, every country. Yeah, don't do this at home. Where'd my colo go? That'll happen real quick. I lost my colo in like a half hour when I tried this without special treatment. You will get complaints. You will get calls from scary-sounding places, as you should. This is behavior that normally precedes an attack. Why am I doing it? Because it kind of doesn't make sense to me that the bad guys should have better information than we do. I mean, I don't want to be running defense as an idiot. So I'm trying to collect use our one advantage as white hats, as good guys, as, you know, we can go out there and we can make a bunch of noise and we don't need to hide because that's sticking me in prison. Cool. So what have I been doing to make this feasible? Reverse DNS. So when you do a lookup on it, it actually says, hi, here's who I am. When you go to the website at the URL, it tells you how to get in touch with me, how to reach me, who I am, why I'm doing things. Generally, the idea is if I'm going ahead and making it really easy to arrest me, maybe you won't. I actually got Aaron updated. You do a who is on the IP range, and it says Dan Kaminsky Security Research. So this stuff doesn't go unnoticed, uncomplained about. So I think the most amusing contact I got, well, second most, I had to explain in detail what I was doing, and the response was one line, thank you for the information. We will see you in Las Vegas. I'm like, I hope that's for a beer. Early results. So Google was taken out back in March of last year. Not all over the world, but not nowhere either. They were taken out by a attack that was a DNS poisoning attack, and it exploited systems that were Microsoft DNS servers that forwarded up to Bind 8. Now, if you go to the Bind homepage, for the Bind is the largest DNS server in the world, or most widely deployed, they tell you, for the love of God, do not let anything forward to Bind 8. It is wildly insecure. And a bunch of administrators said, hey, that's a nice box in the corner. So in my attempt to kind of point out maybe you should do what your vendor tells you, I decided I'd go out and find all the name servers on the net and figure out how many were vulnerable to this. Well, you know, how did I find them? I ended up using a legitimate lookup. I figured everyone could host themselves. I had everyone look up localhost. Okay, well, everyone knows about that one, I figured. And next step was to figure out which ones were related to which other ones. Now, how do we do that? How do you find a forwarding interrelationship? Well, what is a forwarding interrelationship? I run DuckSparrow.com, and I go to Alice, and I say, hey, Alice, go look up alice.DuckSparrow.com. If Bob comes to me looking for alice.DuckSparrow.com, I have a pretty good idea that maybe Alice and Bob are in cahoots. So that's the general idea here. Now, the gold standard way of figuring out if two hosts are actually in some kind of communication between them is to actually use what's called the recursion flag. Now, when you do a DNS request, it turns out that you can ask the server, only give me this information if you already have it. This is as opposed to the normal DNS request, which is, you know, hey, you, go do a bunch of work for me, and when you're done, come back and tell me the answer, thanks. So you can actually just say, hey, if you already have this, go get it for me. So what you do is you tell one guy, hey, you, go out and do a bunch of work. Now I go to everyone else in the room, and I see if anyone else has the results that he was supposed to give me. If someone else has the answer, I bet he didn't do it himself. I bet he just told one of his buddies to do it. Exactly. So there's a little problem. It's ungodly slow. I go to him, and I tell him to do a bunch of work. I have to go to you, go to you, go to you, go to all of you. And then, you know, I have to iterate, you know, for 100 people, I need to do 10,000 lookups. For the 2.5 million name servers I was trying to look at, that's not going to happen in my lifetime. So there was a modification that I figured out, which is it turns out when DNS data comes back, there's a time to live value that actually is decremented from when the server first got that information. So let's say the time to live value is 3,600 seconds, is 1 hour. And I go to this guy, and he gives me the correct information. But he gives it to me with a 3,500 second time to live. Well, let's see. Why would it be 3,500 instead of 3,600? Let me do a little bit of math here. Yeah, it's 100 seconds ago, he went ahead and got the data. So what I do is I look to see who was I scanning 100 seconds ago. Because whoever I was scanning 100 seconds ago told this guy to go out and do a lookup. And this guy got it in his cache back then. So That's a much, much faster way of doing things. It has a few issues in terms of weirdness with how certain hosts manage their TTLs. So the answer ended up being what I first told you. That whole, hey, I go to Alice, I say look up alice.docsparrow.com. If Bob comes to me, I know Alice and Bob are in cahoots. I mean, that's the way that it works. And you end up being able to throw this all into a database, do a stupid little query, and you just get the answers. So it works really well. What did I find? 2.5 million named servers out there that actually were verified, that were reliably communicating with me. Reliably is odd. They tend to fly around a little. I went ahead and read, I was going to write a DNS fingerprinter myself, but there's a guy, Roy Arends. Someone have a time, what time it is right now, by the way? Okay, good. Just trying to keep track. I have a lot of stuff to show you guys. They're pretty. So I was going to write a DNS fingerprinter, but it turned out completely unnecessary. Roy Arends has written the DNS fingerprinting tool to use. It's called FPDNS. It's absurd. And yes, I ran it against all 2.5 million servers twice, once in July, once in November. And went ahead and figured out, well, here's what every IP's operating system is, and here's how every IP links to every other IP. So let's find every system that actually matches the Google case of forwarding to bind 8, and especially Microsoft forwarding to bind 8. Now, I didn't expect that many to be vulnerable to this problem. I mean, I figured forwarding relationships were kind of weird, obscure, rare, not 10% of the DNS infrastructure. Oh, crap. Apparently, lots and lots and lots and lots of places will have bind 8 forwarding to bind 8. 13,000 places will have Windows forwarding to bind 8. There was a total of 230,000 systems that had this vulnerable configuration. What the heck? So I'm actually working now on dealing with getting the information out. The problem with finding vulnerabilities on this scale is, let's say only 0.01% of the administrators out there would sue you into the ground for telling them that they had a problem. Let's see, 0.01% of 230,000 is me a small spot on the ground. So there's a lot of work going on to be able to do notification. There is some other stuff. I did find some evidence of DNS poisoning. This is funny. Reverse lookups. So anyone here know about, who here knows what a reverse lookup is? I love Europe. Holy crap. So here's the, so for those of you who don't, normal DNS, given a name, get the number. Reverse lookup, given a number, get the name. Now, the actual mechanics for how reverse lookups work are actually very similar to DNS. You know, you have some hierarchy, you go from host to host to host to figure out, eventually you get to a machine that is able to do a reverse lookup for you, what's called a pointer lookup. Now, most of the time, your ISP is going to handle the reverse lookup for your particular name. Now, in this case, I am the ISP, so I handle my own reverse DNS, which means when I'm flooding traffic across the internet, when, say, some people are investigating who's flooding traffic across the internet, a bunch of them see me. So I found about 38,000 hosts that will actually automatically do reverse DNS lookup. Actually, no, a bunch of them were automatic and a bunch of them weren't. I'm not sure which were which, but I can say that I did see traffic from networks I ain't ever seen traffic from networks from. So, and it turns out it's even possible to figure out which IP addresses caused which at least automatic lookups by randomizing your source. So for the forensics people in the audience, guys, be really careful when you do reverse lookups, because you leak. Going a little deeper. So, most interrelationships are shallow. That was what I thought. You know, figured, you know, you might have a bunch of machines that are talking to one guy, or, you know, might have like little stupid relationships. And, you know, I was totally right. In like 40,000, actually no, in the majority of cases, if I ask Alice to go look something up, Alice goes and looks something up. Now, there are about 40,000 what are called connected graphs that are hosts that are in some kind of shared relationship with one another. And these 40,000 systems, this is pretty much what I expected. It looks like, see guys, this is why I wanted the lights maybe to be dimmable, but it doesn't matter, you can kind of see. You'll get like some little host in the middle, and then all these guys around will go out to it. And you'll get this guy and then all these guys. And you might have a couple clusters that communicate with one another. Nothing surprising. And there's that guy. Yeah. 220,000 node, 330,000 edge, 22 deep. There's a name server out there that if I send it a request, one of 1,000 different IPs comes back to me to service that request. I have no freaking clue what the hell this is. This is not supposed to exist in DNS. The data is really compelling and pretty. So I don't know what's going on. Now, raise your hand if you've seen the picture on the right. Ah, yes. Now we're going to move into even more fun with DNS. As some of my friends said, oh my God, Dan, that wasn't actually supposed to be useful. So, how many people here have heard about the little Sony stuff that's been going on lately? Ah, now you guys raise your hands. So here's the deal, right? So Sony did a little bit of a bad thing recently. Placed malicious code on like a couple million CDs that they're admitting. It's really funny. Some people think that this malice was contained just to the cloaking code. No. The malice is on the rootkit. Not on the rootkit. The malice is on the DRM. Like, it actually is from a security standpoint. Here's the deal, right? Overstayed welcome. If you're my friend, you can be my best friend in the world. You refuse to leave my home, you're not my friend. If you do that to all your friends, suddenly you have no friends. Sony did kind of the same thing. They released software that they wanted to get in through as little consent as possible, if that, if any. And once it was there, they wanted it never to go away. That's why there was no uninstaller that it shipped with when, most Windows code has uninstallers, not this one. It's very rare you have to beg online for an uninstaller. You needed to beg for this one. How many times have you seen 3 uninstallers necessary for a product because they keep their hand in the cookie jar? Oh, I've only heard of it in this case. So, the idea is there was a way that they wished computers operate, and that's nice. I want a pony, but you don't get to go ahead and modify the entire computer infrastructure to be what you would like. And what was their solution to the claim? What was their solution to, well, people will want to get rid of this? Well, they won't want to get rid of it if they don't know it's there. That is why it's not just a rootkit problem. The rootkit goes to intent. The rootkit shows that they intended to go ahead and have software that would run without user consent. That is why the security community has reacted as violently as it has. That, and for the love of God, we cannot fight multi-billion-dollar companies playing the hacking game. So, in case anyone thinks this is not like active policy, the music industry will take whatever steps it needs to protect itself and protect its revenue stream. It will not lose that revenue stream no matter what. Sony's going to take aggressive steps to stop this, etc., etc. Sony Picture Entertainment US Senior VP. So, I'm just saying, we see what they did, we see what the implications are, and then there's Steve Heckler. Okay. Get this stuff off. There's a problem, though. Get this stuff off what? I mean, Sony sure as heck isn't going to tell anyone what's going on here, how many systems are infected. What if we're wrong? What if we found a rootkit and no users were actually dumb enough to install it? I mean, that'd be fantastic, right? I mean, how rare is it in the security community that, like, problems are better than we thought. I mean, that's like a rare gift. I would love to be wrong. I really would. So I wanted to know how many systems were actually affected by this stuff. Because if it was like 1 or 2,000, who cares? We get those 1 or 2,000 people fixed, and we don't need to make that big of a deal of it. But what if it's a worm scale infection? Okay, then maybe. But we had no data. Well, we had no data from Sony, no accurate data. But that's understandable. I mean, they did do something criminal. You usually don't talk. It's kind of what your lawyers tell you. Microsoft could have found out, but there's a little bit of massive drama going on right now with the HD DVD versus Blu-ray versus what features Blu-ray will and won't have. I kind of see where Microsoft is coming from not, showing off just how bad the problem was. The real question is the antivirus vendors. Sony went to unnamed antivirus vendors that you can look up on Google. And that was about the first reaction they had. And what was the first press release? Sony talking to these antivirus vendors. I don't know the last time I've heard of an antivirus vendor talking to a virus author in terms of like, let's negotiate how we can keep your stuff on lots of machines. I don't mean to be rude, but that's not exactly what they pay them to do. I thought we figured this out with spyware. Keep our systems safe or go away. So what Bruce Schneier basically said it best. What do we do when the makers of malware are colluding with the very people we pay to protect us from malware? Rather than waiting for someone to finally give data, I kind of realized I can go get the data myself. So here's the deal, right? All disks with the XCP Aurora rootkit also had some code that went out and connected to Sony-owned sites, this connected.sonymusic.com address, among some other names. Now, the internet doesn't run on IP addresses. You can't just like throw that in anymore. You can throw a name into the phone network. You have to have numbers. And that's what DNS gives you. It gives you these numbers. And so I thought about it. I'm like, well, you've got all these people, and they're doing all these lookups. And all these lookups are going to Sony if they've got the rootkit. And all these responses are coming back. These responses are cached just in case they'd be useful for someone else later. I wonder who else they might be useful for. Oh, yeah. If only I had, like, a list of every named server in the world. Yes. They could hear me cackling from several miles away. And even better, there's this mechanism, what I was mentioning earlier, the non-recursive lookup, that would go ahead and go get the data from the name servers only if it was already cached. So I wouldn't even be like polluting the data set. Now this isn't a method I created myself. Louis Grangia went ahead and wrote this fantastic paper, DNS cache snooping for fun and profit. And I looked at it and thought about it and was then like, let's do that like a couple 100 million times. And back in November, I basically spent an entire weekend, I was partying and the computer was scanning and every, every 16 hours I looked at the data, I'm like, no, that can't be right. Yeah. So what'd we find? 556,000 hosts that were saying either connected.sonymusic.com, updates.xcpaurora.com, or a little bit of the Suncom addresses. It turns out I even had more. Well, I'll give you some of the constraints later. This is really weird. There's data from 165 countries. These discs are only supposedly sold in the US. How the heck are we getting outside? The best theory we have now is, well, how did we get here? We got here through CD piracy, through music piracy. What if a bunch of the infected discs are from pirates who copied the discs and exported them out of the US and kind of pirated the rootkit as well? I I really don't know what the legal implications of that. Wouldn't it be funny if Sony was actually not responsible or did not ship most of the gear that infected systems had? I don't really know what to think about that. So then the next thing I did is I actually went ahead and made some maps. And because I have limited ability, I actually have all of 50 minutes battery life in this until Dell sees it the next time. But I went ahead and made some maps and actually threw them on a globe as to where these infections were. Let me tell you, if you ever have like data on this scale, throwing it on a globe is awesome. And it's actually not hard. If you send me an email, I'll send you the code that, given some XY coordinates, will go ahead and throw IP addresses on a map. You do have to go ahead and get the buy the data source. It's like $500 for the database. But it's certainly been fun. So now we got some noise. Well, talking about the noise that I got rid of immediately. It turns out, even though the specifications say when you have the recursion desired bit set to 0, it will only give it to you out of its cache, there are in fact a bunch of servers that will go ahead and do all this work anyway. You said, hey, just give me the information if you already have it. It goes out and says, well, you know, I'm just going to do it anyway. It might be useful. So, I accounted for that immediately because I doubted my own data. I mean, this is too big. And I actually found 900,000 systems that were reporting the Sony data. But really only 350,000 of them would do lookups that I know, couldn't have happened otherwise. I did unique lookups against names that I controlled. So I filtered those out, and I've never claimed that. I mean, they might be involved. They might have had lookups, but I can't reliably say they definitely do. Also filtered out servers that had incorrect records for names, which we'll have for a bunch of captive portals. Any servers with fixed TTLs, meaning that are divisible by 100. The idea being that, well, if they're divisible by 100, they probably went out and got fresh data. So I mean, I really did what I could to filter stuff. What was actually a really big problem that I didn't find out until after I did the announcement, though, was that one of the sites, this updates.xcpaurora.com, very, very popular name, supposedly directly connected to by the rootkit. I had two sources that both verified, yes, the rootkit actually does go there. Me, of course, not wanting to touch the rootkit because we have that fun law called the DMCA that, I don't want to be ground into the ground. It didn't actually go there. The rootkit itself, the cloaking code, actually has no network components. It's just other code that is on the same disk that goes ahead and connects to the network. This is absolutely amazing. In fact, this is probably the most interesting story. There is a massive correlation between users who thought they might be infected and users who tried to get rid of this stuff. Whatever we thought about this being something that just scared the geek community, I don't think this much DNS traffic could have come from just geeks. This was a very big story that a lot of people really were paying attention to, and that's astonishing to me. Now, my data wasn't perfect. What was the thing to do? Well, let's get more data. So guess what, guys? You're the first to hear. I actually never stopped scanning. That was back in November. Gigs. Tens of I have like 85 gigs of compressed packet logs. Anyone says I don't have data, I can't even get the data to my home. It's on a DSL line right now. It'll like take about a month and a half to ship it all over the wires. I'm sending the guy a hard drive. My database has 36.6 million records. It's awesome. So what did I end up finding through all these scans? I did go ahead and look at the Suncom MediaMax stuff. Nowhere near as much deployment. So there are two addresses. This license.suncom2.com address, I only found 57,000 servers. However, the TTL on that data was set to 600. So I found 57,000 servers that had that data retrieved within the last 10 minutes. Cool. The other thing I went ahead and did was we looked up anyone who knew about this Suncom2 address at all. It was called the DNS any lookup that says if you have any information on this, go ahead and get it. Now, amusingly enough, Suncom2 has name servers that have to have names hosted by the root servers. And the root servers have better things to do than send out fresh data every 600 seconds. So even though license.suncom2.com was defended against DNS cache snooping, the root servers were handing out records with lifespans in the 131,000 second range. So no problem. So I found about 115,000 servers that knew about something in the Suncom2 domain. Cool. But the real goal was to go ahead and get better information about XCP. And around December 15th, J. Alex Halderman, who's been one of the other big people who's been looking into the rootkit, sends me an email. And he says, hey, Dan. I go, yeah. He's like, hey, you know, have you actually looked what happens if you have a Sony rootkit disk and you go to Sony? I'm like, no, I've been trying to avoid any of that. And anyway, they took it off the shelf. He's like, well, when you go and get it, it sends you back a redirect to xcpimages.sonybmg.com. Oh. So I went ahead and 10 minutes later started sweeps on XCP images. Not only that, there's also cp.sonybmg.com. Went ahead and started sweeps on that. Hey, look at this. I went ahead and, they're actually all tied to this UID field over at the top. Huh. That's a monotonically increasing number that seems to be kind of small. So I did about 2,000 wgets and got all the possible names. And what did I find? I found, hey, look, 52 IDs. Go to XCP Images. What does Sony say? 52 disks have the XCP software. Sweet. 85 IDs had cp.sonybmg.com/XCP. I have no explanation for that. So what did I find from this data? Well, 362,000 name servers reporting XCP images. The name that is theoretically a perfect map to anything with XCP. Excellent, that's within an order of magnitude. 424,000 going to cp.sonybmg.com. Now this is actually kind of interesting. It took me like 5 or 6 days to go ahead and find enough servers to, to find 362,000 servers reporting XCP images. Okay. I had almost all 424,000 servers for cp.sonybmg.com. I had that in like the first day. The really nice thing, by the way, of doing full packet logs is I know I have like a year's worth of data analysis that I can do on this stuff. So, and anyone wants to doubt me? Here's some data. So what's the conclusion here? So upon further extensive data collection, because, seriously, I wanted to know if I was wrong. It'd be like a Christmas present. Hey, guess what? The internet is safer than you thought. Excellent. Every available sign of data, the rescan, the reanalysis, the improved metrics, all go ahead and point at the direction of A, yes, this is a worm-scale infection with hundreds of thousands to millions of infected nodes. And B, and most mysteriously, this is absolutely an international infection. And I am going to talk about the banner ad for a second, because that's actually important. So let's look at what the country data is on this. We've got 142,000 infected or reporting nodes in Japan that report on this stuff. We've got 100,000 in the US. We have 70,000 in Europe. There's actually 4 name servers here in Berlin that actually reported back to me and said, oh yeah, someone from here went ahead and had the XCP software. This is with completely new data, completely new scans. I have no idea. Now, it's important to see the banner ad because the banner ad is actually excellent. When you put in an XCP disk, it goes ahead and tells you, yeah, sorry, we tried to hack your machine. It was there, it was possible. Ethics are for other people. And so, not all the things that went ahead, in fact, hopefully, a good portion of those that are now reporting XCP images actually went ahead and ran the uninstaller. Only Sony knows, but they're certainly not talking. What the conclusion was always trying to get back to is saying, is this something that's at the scale of 1,000 to 10,000 hosts, or is it at the scale of the hundreds of thousands to millions? And, the fact that to this day, this long after things have been taken off the shelf, after uninstallers have been put on, after all this is going on, that we're still seeing, this much traffic says absolutely. This is a worldwide issue. We need to treat it like we treat any worm and do, ask our antivirus vendor why they're not fixing the problem. So I, of course, have more and more work to do. Analyze records, identify IP addresses where a DNS server will hop from host to host. There's so much weird stuff in DNS. Try to get a handle on it. And you know, it's possible it's going to revise numbers down, and that's good. I'm on a constant goal to get better data. When Sony cooperates, I'll have even better data. One of the big things I want to do is I want to schedule my traffic better so that I am less likely to go ahead and flood out networks. And what time is it right now, by the way? 50. Oh, wow. OK. Well, I'm going to skip this part because this part doesn't have nearly the pretty pictures. But come to me later if you want to hear how you can reliably sweep the internet for stuff. So after you go ahead and do huge sweeps of the net, you get some pretty crazy looking graphs, which really are kind of hard to see. But graphs are cool. Graphs go ahead and represent interconnections between hosts. Now, the only problem is that, well, light or not, you can kind of tell that's a big mess of stuff, but what the heck is it trying to tell us, and how the heck does it reflect anything that is in our normal experience? So one of the things I've been wanting to do is to get an idea of what traffic looks like in real time. So I used some code from this thing, the Boost Graph library, written by Doug Greger. It's generic, exceedingly fast, and it lets graphs, meaning there are hosts and then there's where they go to, where the links are, nodes and edges, go ahead and make pictures. Well, Boost supports this thing called the Fruchterman-Reingold layout engine. And Fruchterman-Reingold is fantastic. Why is it fantastic? Because you can throw utter crap into it and it will render. It will not crash. You'd think not crashing is a big deal, but oh no, it's a huge, huge problem. Things love crashing. Just ask Dell. All right, so if this ever works. Okay, long story short, we're on a really cool network here. It has a 10 gig pipe up for a conference. Dear God. If you ran TCP dump on this network, you wouldn't get anything useful. So what I wanted, so I went to the network guys, and Niels and Alex went ahead and built this like immediately. Real-time graphs of the network here at CCC. Who's connecting to what? I have no idea if this is going to work. Oh, it worked the first time. Life is good. So, now, for whatever reason, I'm actually not getting that much traffic from, this is real traffic. This is live. I mean, oh, wait. Oh, sweet. It's addictive. So yes, eventually I'm going to go ahead and let's look at some other data I have here. So this is off a backbone. Actually, earlier today, this is exactly what the CCC network looked like, right? I mean, just huge amounts of these little clusters linking to each other. The input is so trivial, but I'll show it to you in a sec. We can actually put things in 3D. By the way, Merry Christmas. This is being released here at CCC. So, all right. Got to reserve what little power that thing has left. Oh, I'm going to have a fun call with Dell later today. I can't wait. So, static images. God, oh well. So, this is available. This is free. This is BSD licensed. Do whatever you want with it. And the only request, if you do really cool things, let me know, because I like seeing cool things. Now, The input is kind of hard. You might have a difficult time working with it. You have a text file, A, B. Yeah, you just basically stream text descriptions into it, and it figures out the rest. It'll go and, oh, I've never seen that node before. Let's go ahead and make a new one. It just does it. You know, I build this thing so I can SSH into remote hosts, run TCP dump, run it through a stupid little cut, and pipe straight in. It is a streaming graph visualizer. It is built to not suck. Stuff that I want to get done on this. Well, first of all, you know, I want to get directed graphs. There is a demand for the network team. Apparently, you guys are slacking. They went ahead and they brought you a 10 gig pipe. You're just not going to deserve that fiber to the home if you don't go ahead and use fiber to the con. So, things that I want to get done. Directed graphs should appear directed. If one host is talking to another, you should be able to see it. I do have a cute little stunt that I did, though. Remember when I tilted the graph and put it into 3D so that, you know, some things were high up? Well, they could be high up, but they could also be down lower than the base plane. The idea is that the number of hops that something's going out to determined how high it was. And the number of things that was coming into a host was how low it was. So if you had, so what it is, that's not commutative. If you have way more things coming in than going out, it's going to be below. Way more things coming out than going in, it's going to be high. So that was one way that I got some way to render that piece of information. But it really should be possible to see what direction links are going in. I really should be able to do comparisons very easily, be able to say, well, here's a graph for all the BitTorrent traffic versus the port 80 traffic. I want to go ahead and have active highlighting really badly. I want to be able to move my mouse over a region and have it go from just, hey, that's a pretty picture, to, here's all the information on this cluster you've highlighted. Sweet. So there's a bunch of work that's going on here. I would very much like to work with people on this, especially demo scene people. And demo scene people see my poor OpenGL. Incidentally, the demo scene is awesome. That is some hardcore crazy code you guys are doing. So I'd love to see like security in the demo scene somehow do an alliance for this kind of stuff, because that'd be just rad. So why use graphs? This is actually kind of an interesting thing. They are actually more than just pretty pictures. You know, now that we have all this data, you know, in a graph formation, in an idea where I can do logical operations of, hey, this connects to this, connects to this, connects to this, connects to this. Remember I was talking about how it would be really nice to be able to schedule my scans so I don't take down networks by flooding too much traffic through them? Well, once I go ahead and can do large-scale internet scans and large-scale analysis of stuff with an awareness of all the paths that are available, I can actually start scheduling an individual transmission based on what the impact to the network is going to be from end to end. So I can go ahead and schedule all my outgoing DNS scans, all my outgoing network scans, and it will all say, hey, I want to make sure I don't get 15K a second more on any link, and I want to make sure I don't overload anything. And best yet, I can go ahead and now figure out what are the set of most useful hosts that it would be for me to start actively monitoring. Well, let's see. I go ahead and I have this entire topology in front of me, and I know if I go in that direction and I have a TTL of 8, I should get responses back from this particular host. If that host ever changes, the topology has changed on me. If those pings, if those responses stop coming back to me, I know I'm overloading traffic on that link, and I need to go ahead and rewind a certain number of packets. So what started as, let's get some pretty pictures going, has turned into, hey, wait, we have an entire logical organization here. Let's use it. So that's my stunts. That's what I'm working on. I was going to show you video over DNS stuff. Just believe me that it works. And if you have any questions, that's my email. And if we've got some time, let's chat.